Hello. With this video, we begin our unit on spontaneity, entropy, and free energy as described in chapter 17 in the textbook. This chapter could accurately be named chemical thermodynamics because that really is what we're talking about, the field of thermodynamics as it applies to chemistry. So, thermodynamics is defined as the study of energy changes in chemical or physical processes. As you know, pretty much every chemical or physical change involves some corresponding change in energy as well. In this unit, related to chemical thermodynamics, we are going to answer the question, why is it that some processes are spontaneous and others are not? It will also let us quantify spontaneity. That is, tell us how spontaneous or not a process is. And what numerical quantity do you think that pertains to a particular chemical reaction tells us how spontaneous or non-spontaneous it is? Well, if you think about it for a minute, you'll realize that that number is K, the equilibrium constant. All of this basically tells us how the equilibrium constant depends upon temperature and other features of the chemical reaction. Now, my favorite diagram in the textbook is one that I showed you back in chapter 12 when we talked about kinetics, and I'll reiterate it here, and that is essentially one that demonstrates the difference between the domains of thermodynamics and kinetics. The domain of thermodynamics is simply the initial and final states. All thermodynamics cares about is the relative difference in energy between the reactants and products, because as you will see, that is entirely what determines whether a process is spontaneous or not. In thermodynamics, we do not care how you get from reactants to products. All that matters is the absolute difference in energy. Kinetics, on the other hand, didn't particularly care whether a process was spontaneous or not. All that we cared about is the pathway or mechanism, how you got from the reactants to the products. In this unit, we don't care about that. Again, it's only concerned with the difference. Now, in our first section, we're going to talk about spontaneous processes and entropy. What is a spontaneous process, and what are some examples? Well, a spontaneous process is defined as one that occurs without outside intervention. You do not need to do anything in order for the spontaneous process to occur. It simply happens because the final state is lower in energy than the initial state. And a general rule is that all processes spontaneously proceed from a state of higher energy to a lower energy. Okay? So for example, a gas spontaneously expands into a vacuum. A ball rolls down a hill when you release it. A hot object placed in an environment of lower temperature cools down. Iron, in the presence of oxygen, rusts. These are all spontaneous processes. Is spontaneity related to rate? To say that a process is spontaneous, does that mean it happens rapidly? Obviously no. I just got finished ranting about how thermodynamics and kinetics are unrelated to each other. To say that a process occurs without outside intervention does not mean that it happens rapidly at all. It could be painstakingly slow. Does the reverse of a spontaneous process ever occur without outside intervention? Again, obviously no. If a process is spontaneous in the forward direction, it would be non-spontaneous in the reverse direction. And here's a question. What is it that makes a process spontaneous? Well, for a long time, people thought that if a process released heat energy to its environment, it would necessarily be spontaneous. Okay? So exothermicity, is that what's required for a process to be spontaneous? And the answer is no, because it is possible for endothermic processes to be spontaneous. And in class, I will demonstrate to you, and you may have seen in your own life, examples of endothermic reactions that actually occur without outside intervention. And I just realized I misspelled endothermic. There we go. Okay? So here is the primary criterion for spontaneity. Are you ready? The driving force of a spontaneous process is an increase in entropy of the universe. So, when every spontaneous process occurs, the entropy of the universe increases. So now, let's talk about what is entropy. Entropy, in reality, is a thermodynamic function that is related to the number of arrangements available to a system in a given state, meaning how many positions and or energy levels the particles can be in. That doesn't mean much from our point of view. we're going to think of entropy as being a measure of molecular randomness or disorder. High entropy corresponds to a great deal of disorder because there are lots of ways of arranging the particles, whereas low entropy means lots and lots of order and organization, meaning fewer number of arrangements. The more possible arrangements there are in a system, the higher the entropy. Or another way of thinking of it is that if we specify a state, the more ways that a state can be achieved, the greater the probability that we can actually find that state. And it is the case that nature proceeds spontaneously towards states that have the highest probability of existing and therefore the greatest entropy. Now, we can actually measure entropies of systems, and the symbol uppercase S is the quantity symbol that we use for entropy. I don't know where it came from, but that's what we're going to use. Okay? So, for example, water in the solid phase, ice, has a standard entropy of 41.3 joules per mole per Kelvin. Liquid water has a standard entropy of 69.9 joules per mole per Kelvin, whereas water vapor has a standard entropy of 188.7 joules per mole per Kelvin. As we go from solid to liquid to gas, the standard entropy of water increases. In fact, it's always the case that the entropy of the solid is less than the entropy of the liquid, which is much less than the entropy of the gas. Does that make sense? Well, it certainly does, because as we go from a solid to a liquid to a gas, we are going from less randomness, or more order, and therefore lower entropy, to greater randomness, greater disorder, and therefore greater entropy as well. It is always the case that the entropy of a separate solute and solvent is less than the entropy of the corresponding solution. So when we dissolve a solute and a solvent, we give the particles now in solution more room to float around in. There are more ways of arranging those particles, more possible arrangements available to the system, and therefore higher entropy. It is always the case that for a given system, the entropy is greater at high temperature than lower temperature because the particles are moving around more. And we can calculate for a given process the entropy change, delta S, which is the entropy of the final state minus the entropy of the initial state. If for a given process the change in entropy delta S is positive, that corresponds to an increase in disorder or randomness. Whereas for a process, if delta S, the entropy change, is negative, that corresponds to a decrease in randomness or an increase in order. So, which of the following processes are spontaneous? Which of these occur without outside intervention? A house is built? Nope, got to intervene to do that. A satellite is launched into orbit? Nope, that takes outside intervention. A satellite falls back to Earth? Absolutely, they all will at some point. The kitchen gets cluttered? That happens spontaneously, at least in my kitchen. Which of the following involve an increase in the entropy of the system? So in which of these is delta S positive? Meaning, for which are we going from more order and organization to more randomness and disorder? Melting of a solid? Certainly. From solid to liquid, that involves an increase in entropy. Sublimation of solid to gas? Sure. More disorder in a gas than a solid. What about freezing? No, that's going from a liquid to a solid. That's actually decreasing the entropy. Mixing? Sure. Randomize the particles. That's a positive delta S. Separation? No, I don't think so, because we're going from more randomness to more order. Boiling, going from liquid to gas. Yes, certainly that involves an increase in the entropy. Okay, that's all for the introductory section. In our next video, we will talk about entropy changes in chemical reactions and how we actually calculate them.